Very good morning to all of my listeners. Myself, Deepak Sahu, Assistant Professor in IIMT College of Engineering, Greater Noida, Electronics and Communication Engineering Department. So, learners, today we'll be discussing a very primary and basic topic of analog electronics, uh, which is mainly analog filters. Filters are basic fundamentals of an electronic circuits, particular in audio and video electronics. And in due courses of time, analog electronics refine themselves or improve themselves in the form of active filters, which mainly incorporates the working of op-amps in a particular fashion, such that they allow a particular set and ranges of frequency, which we know as in terms of bandwidth. So, first we will see here uh, an outline of today's presentation, a basic introduction, then advantages of active filters over passive filters, then brief summary and type of filters, filter response characteristics, and for today's lessons, we'll be discussing mainly active low-pass filter and active high-pass filter. And furthermore, like band pass, band reject, notch filters, we'll be discussing in subsequent uh, lectures. Now, basic introduction. Here I have noted down in the form of points. So the basic and most fundamental definition of filters is that there are a particular band of frequencies which are either allowed or stopped or blocked in a particular set of ranges. This frequency selection or bandwidth selection is also known as frequency selectivity. Now, earlier they were passive filters in which filtering capability was present, but as every electronic circuits is a part of a universal system in which there is an input and there is an output, and we all know that very few systems, or ideally no practical system, shows 100% efficiency, which means output signal strength will be a more or less than input signal. Now, in particular case of audio and video transmissions, as signals are actually within a very small range of amplitudes or magnitudes. So, attenuation of signals occurred while having a frequency selection. So that was a mainly drawback of passive filters. In that, active filters actually remove these issues because op-amps incorporate an open loop gain in them. So if we current components and op-amps in a certain fashion, they both give frequency selections and bandwidth, and in terms also the whatever attenuation was occurring due to the systems, they all to help to improve and maintain signals amplitude levels. Now, in the most current systems, basically all passive filters have been removed by active filters, that is op-amp based filters. And their physical advantages also that since op-amps are very light-weighted and they are more robust in a sense. So all range of electronics, particularly audio and video, have started using active filters. Now, as such, there are many advantages, but to present a few of them. First is what we just discussed. The active filters can be designed to provide required gain, hence no attenuation was observed. Now, this is a very interesting term. A loading issue. No loading problem has been discussed here. For our learners, in our earlier lectures, we have discussed in multi-stage amplifier systems how does loading affect the overall performance of the gain and how we incorporate systems to handle these issues. Now, active filters, which I just told, op-amps are very cost-effective and light-weighted. So physically, they are easy to incorporate and in electronic circuits, whether it is portable or fixed. And also, since op-amp ICs are very, very cost-effective, so designing circuits using op-amps IC are also very cost-effective. Now, basically, active filters can be particularly summarized in the form of these four categories: low pass, high pass, band pass, and band stop filters. Now, all four systems are having an open loop gain, which is primarily shown by the symbol A naught, and RC-based systems, which actually helps in frequency selection. Now, frequency response characteristic curve had been discussed here. We can clearly show that on a y-axis, gain in decibel is mentioned, and on the x-axis, frequency ranges are covered. And here in a shaded region, passband, which mainly incorporates bandwidth of a particular filter. And now there is a roll-off factor, which actually is our main issue, because roll-off factor, that is region after cutoff frequency, has to be very narrow, so that it does not incorporate any noise or absorb any noise from nearby systems. So roll-off factor needs to be high. As high as the roll-off factor will be, sharper the slope of filters will be that, and very refined cutoff we can obtain. Now, firstly, only two topics will be discussed here: low pass filter and band pass filter. Two curves are shown, gain versus frequency curves. An ideal curve is shown here with a very sharp gain in a passband and a instantaneous decrease in gain after the cutoff band frequency. In the left-hand side, a practical implementation is there. We can see that the passband is more or like an ideal case, but the instantaneous drop in gain does not become zero. It covers much more range after cutoff frequency. The problem with a long range roll-off factor is that after the cutoff frequency, which is our useful frequency, which we needs to filtered out or we needs to be kept. If other frequencies are also covered with a high gain ranges, then they will attract unwanted noise and chirpy disturbance sound in the systems. Now, for a particular circuit shown here, it is a first order low pass filter in its passive form. This is a basic and RC circuit in which output is being obtained across a capacitor. So now here we will have taken a very basic Laplace transformations and a voltage divider system. So we have obtained a transfer function in the form of cutoff frequency and fixed frequency. Now, as you can clearly see in the modulus of gain formula, on the left-hand side, absolute gain is mentioned, and on the right-hand side, gain in decibel is mentioned. So in the earlier curves we have seen, like in the blue region, we can see clearly that on a y-axis, gain in decibel is shown. So after obtaining gain in absolute form, we can use the formula 20 log absolute gain, and that gain will be converted into decibel frequency ranges. Now, to roughly plot any filter frequency response curve, Mainly, we will take three critical points, that is omega at the starting 0, then in a midway when varying frequency will be actually equal to the cutoff frequency, and a very large range of frequency, that is infinite frequency, and we will take down the various salient points so as to get a brief idea how the nature of curving moving on. For example, on our first or low pass filter, we can clearly see here that firstly we have taken omega equals to 0, and omega naught here represents cutoff frequency, which is a constant for a particular filter. Omega will vary. So omega is 0, this gives the highest gain, which is 1. If we convert this gain into decibel, it will come to be 0 decibel. So if we look at the earlier graph, then the highest point here on the left-hand side of graph is what? 0 decibel. Because 1 in absolute value comes to 0 decibel in decibel form. Now, another point we have taken, omega equals to cutoff frequency. We can clearly see 0.707 value of absolute and decibel minus 3 decibel graph. So it is here at this frequency that when the main gain drops about minus 3 decibel from 0 decibel position, then if we take a projection on the x-axis, then we get actually bandwidth. And frequency ahead of this frequency needs to be filtered out very sharply, which is obtained in the form of high roll-off rate. We can see here the purple color represents a straight line approximation, and a dark black line shows the absolute plotting graph. Now we can clearly see the 0 decibel position and minus 3 decibel position, and where minus 3 decibel position is projected on the x-axis, we have taken that to be a passband. This passband is the actual frequency which will be actually utilized for the low pass filter circuit behavior. And any frequencies falling apart from them, its gain should be very sharp. For example, if slope is at 10 times of frequency, we can see that slope is still much here. So this additional frequency range will incorporate noises and will disturb the smooth functioning of filter. Now, to increase the roll-off rate, order of filters needs to be improved. So order of system is decided by the frequency dependent components. For example, if there is an RC circuit and a single capacitor is there, then it will be incorporated as first order. If there are two frequency-based energy storing elements, like here in this diagram, two capacitors are shown. So order will become second order filter. After frequent subsequent solving, we get transfer function as shown on the upper left-hand side, omega naught square upon s square plus. Now, if we see the graph's position of 20 decibel and 40 decibel decade, we see a much sharper turn in frequency. For example, if we particularly look at the graph, now if we take the projection of minus 20 decibel, it will roughly comes to be 9 times of cutoff frequency. But in the earlier, where slope was 20 decibel, that frequency range covered a much more, approximately 10 F. So we can see here, as the roll-off factor got improved, we saved a bandwidth. We should not use the term saved, but have a reduction in the unwanted frequency about from 2 times. So as slope of factors increases, for example, if we see here, look at the cursor screen, minus 20 decibel is there, and we take a projection downward side, it will come to be approximately 7. And earlier it's called 10 times, so that's a significant improvement here. Now, moving on to our second type filter, which is a high-pass filter. And now in the same comparison form is mentioned, an ideal curve is there, and a practical curve is there. Same 0 decibel maximum response is there, passband is there, and same single pole RC filter. Single pole means here that if we have a single RC circuit, that is considered single pole. And if we have a two RC based system, it will be a dual pole system. As the number of poles increases, roll off factors increases in the range of 10 decibel per decade. Because frequency, we have used the term decade because the frequency range variation is in the form of multiples of 10, as we can see in the x-axis. First is 0.001 FC, then 10 times 0.01, then 10 times 0.1, then 10 times FC. In some literature, roll-off factor is also mentioned as decibel per octave. Either value is sufficient and elaborate enough to discuss filters. Now, first order filter is here seen. Now, the variation is transfer function is seen here. Now, if we look at the graph, and now we place the values I've made in the summary form. Omega 0, which gives infinity, omega infinity 1 or 0 decibel, and net cutoff frequency minus 3 decibel, which means at the starting, gain will be 0. And minus infinity means gain will be 0. And at omega's cutoff, minus 3 decibel. And at omega is equal to infinity, maximum gain of 0 decibel. Now, graph is shown is in the same fashion here. Straight line approximation, dark black gain, and pass band. If you see the pass band is again incorporated when gains drops from maximum 0 decibel to minus 3 decibel drop. Again, second order high pass filter is shown here. Two energy storing elements incorporates a second order filtering system. Now, improvement in slow per decade, 40 decibel per decade, and significant reduction in frequency ranges. Now, to conclude this lecture, a comparative table is shown here in the form of transfer functions. For example, on the left-hand side, a low-pass filter is mentioned. If you look at the transfer function, low-pass filter constitutes of only poles, whereas a high-pass filter constitutes of zeros as well as poles. Now, if we took in the magnitude form, which is shown in the second point, where S is replaced with j omega, you can clearly see the difference in transfer function poles, which actually configures their frequency responses. And lastly, fully transfer function shown of a second order system. So learners, today we have seen how first order and second order filters are incorporated, how their frequency response are tabulated, and the contribution of multiple poles and zeros in the frequency response of systems. And so that's it for today. And in the future coming subsequent lectures, we discuss more elaborate and variables of analog filters, particularly active filters like band pass, band stop, notch filters, all pole filters. There are many varieties. So learners, thank you for listening. That's all for today. And hopefully we will meet again for the subsequent lectures and basic understanding of analog electronics and systems. Thank you, listeners. Thank you for watching. Have a good day.